Let us now consider the second case. In the second case, we will take the negative cycle of the carrier signal. What happens if I take the negative cycle of the carrier signal? So if I now take the negative cycle of the carrier signal, the very first thing that will happen is the change in the polarities. Now my left hand side terminal will be at negative polarity and the right hand side terminal will be at positive polarity. Because of this, the voltage level will simply reverse now. If you observe, I just remove the original polarities to avoid confusion. So if you now observe the negative cycle will be negative on the left terminal, positive on the right terminal. So now negative cycle goes to the anode of D1 and anode of D2. And because negative cycle goes to anodes of D1 and D2, D1 and D2 will become reverse bias this time. And the same negative cycle goes to the cathode of D3 and cathode of D4 through the center tap terminals, and hence D3 and D4 will become forward bias. So this whole situation of the previous case will now reverse. The new condition will be that D1 and D2 will become reverse bias now, and hence we will replace them with open circuit, and new status of D3 and D4 will be forward biased, and hence we will replace them with short circuit. So let us see how the equivalent circuit looks like. In equivalent circuit, D1, D2 will be acting as open, D3, D4 will be acting as short circuit. So as you can see, this is how the equivalent circuit will look like. You can see this time the branches containing D1 and D2 are absent because both the branches are open, whereas we have short circuit present across diagonal branches because D3 and D4 are forward biased right now and they are acting as short circuit. So let us see what will happen in this case, what will happen to the output signal in the form of the input signal. So this is how the equivalent circuit looks like. You can see the branches containing D1 and D2 are absent right now because D1 and D2 are acting as reverse biased, whereas the diagonal branches are present because D3 and D4 both are forward biased. If you now observe the nature of output with respect to input, modulating signal, which is my input signal Vi. Now if you observe the positive terminal of the input signal, which is this upper terminal, gets connected to the negative terminal of the output polarities, and negative terminal of the input signal gets connected to the positive terminal of the output polarities. So you can see that there is again a direct connection between input and output side, but it is reversed. In other words, the input signal will go to the output side, but after it is being reversed from the input side. So I repeat, this is simply because the positive reference terminal of the input side is connected to the negative reference terminal of the output side. So if I want to show the polarities of the input signal on the primary of output transformer, in that case positive is present here and negative is present here. So you can see both the polarities are completely opposite to each other. And because of this, if I define my output signal VO this time, VO will be equal to minus Vi. And this is the second most important part of the working of the circuit. So in the negative cycle, every negative cycle of the carrier signal, output will be input signal reversed, or I would say the input signal 180-degree out of phase. With this much understanding, let us now discuss the waveforms of the ring modulator, and through waveforms we will justify that my output is double sideband suppressed carrier.